Hello everyone, this is Vivek Chandel from TCS Research, and I'm excited to present our work on smart analysis of range of motion of joints using a smartwatch. My co-authors are Dr. Murli, who himself is a professional orthopedic surgeon, and Mr. Avik, who is a principal scientist at TCS Research. This work focuses on ease of usage, both for the patient and the doctor alike, in performing a real-time analysis of range of motion. Before moving further, let's take a look at why range of motion, or ROM as I'm going to call it, why is it important? Now range of motion is, as the name suggests, the angular range up to which a particular joint can rotate in either direction. Now there are well-defined rotations for ROM, and as can be seen on the right, that's me depicting some of the commonly used ones, like flexion, extension of shoulder or of the elbow, internal external rotation of shoulder. Now this particular rotation, it should be noted that it happens completely in a plane perpendicular to gravity, so the horizontal plane, a fact which will be of importance actually in the coming slides. So for assessing the health of a joint, ROM proves to be a great biomarker, and those can be the joints which might be recovering from some trauma, or the patient might be in a post-operative rehab. The doctor might be monitoring the health of their joints and so on. Now ROM currently it's very commonly calculated using a manual device which is called a goniometer, which is a device with two arms, one distal and the other proximal, and the central body of the goniometer, it's graduated with angles. Now another fact about ROM is that the values for a healthy joint, they are very well defined in the medical literature. For example, for shoulder flexion, for a healthy adult, this value should be around 170 degrees. So a proper joint should be able to rotate about 170 degrees, close to 170 degrees, while flexing the shoulder. And similarly for shoulder extension, the value can be around 55 degrees. Now here I'm going to focus on what's out there for ROM in literature, and what might be the facts that are hindering a wide-scale usage of these solutions. So first category of solutions, as we already discussed in the previous slide, they are goniometer based, and the shortcomings are pretty obvious. First of all, it's a manual measurement, so the anatomical landmarks, they may vary from one specialist to another. So these anatomical landmarks may be anything, a point where to keep the center of the goniometer, how to place the distal and proximal arms, and so on. So these might vary from one person to another, and so this variation, the problem is that this variation actually is going to cause a change in the readings from one experiment to another, and that's not good. Now using goniometer, it's a one person dedicated job, so some specialist always needs to be around, or you need to visit the clinic to get your ROM analysis done. And lastly, you can do only one measurement from using a goniometer, and that's going to be at the end of the rotation. So there is no data to analyze the full rotational arc. I mean the data, the full rotational parameters while the rotation is happening, and actually that kind of analysis can be beneficial in understanding the challenges that the joint might be facing while performing the rotation. Now second category of solutions, they use multiple sensors, so the multiple sensing modes, usually the inertial motion sensors on each distal arm pertaining to each joint. So there might be two or more sensors on one arm for tracking the rotation of elbow and the shoulder joint, which again, now this kind of setup is it's not the kind of solution one can make use of using simple off the shelf devices, and again it's limited to specially built hardware, and again probably it's best suited only for clinical environments. Now another problem that is seen in this solution is that first the accuracy suffers as the rotation starts to be made in close to horizontal planes. That is what we have observed, like I showed in the previous slide for internal external rotation of the shoulder. Now the reason for that is because these solutions use kind of a fusion of two inertial sensors, which is accelerometer and gyroscope, where gyroscope can actually tell you the angular rate, and accelerometer can resolve the vertical component, because accelerometer gives the gravity. So using that you can resolve vertical component from the horizontal plane. But when the rotation takes place in horizontal plane, like the internal external rotation that we discussed about, so when such a rotation takes place, there is no contribution of gravity, right? So the accuracy starts to suffer, because in that case the contribution of accelerometer is essentially nil, which is why the reason we have tried to use only gyroscope in our solution, and try to perfect the method in as simple way as we can. And also what we see is that none of the solutions, they have been tested at speeds which are really slow, like under 10 degrees per second, the rotational speeds. Now the point is that actually these kind of slow speeds, they are very common in medical settings while calculating ROMe, especially because usually the joints for which one is required to do a range of motion analysis, those joints are injured and cannot be rotated at very fast speeds. And when the rotation happens at really slow speed, this is where the inertial data is going to show a lot more error than the speeds like 50 or 100 degrees per second or even more, for which actually these solutions, they have actually been tested. Now the third category is the ones using a smartwatch, which we'll also be targeting. And there are very few works which have been done around this, and one of them uses machine learning to train the model using various poses for ROMe, which actually was published in WristSense itself last year. But again, since the model, the deep learning model, it provides output using full rotational data. So the model takes the rotational data at once and provides a single output, which is the angle. So in this case, a real-time analysis again is not possible. So you cannot get the angles in real time while the rotation is taking place. And also what we observed is that the errors go as high as over 10 degrees, which might not be acceptable for the use case of range of motion, which actually requires a very high degree of accuracy. Now there are other solutions too, some of which can actually track users' arm using a smartwatch. But first of all, in addition to inertial, they also use magnetometer sensors, which are not available in affordable smartwatches like the ones which come at a cost of like $250 to $300. And second, the tracking accuracy is not enough to be used for ROMe estimation, which targets an error of under 5 degrees at least, and this actually has been suggested by our medical specialists. Now here are some of the key ideas that we have tried to enforce in what we are proposing as our solution, which we call ROMeasure. So first, using only a smartwatch, and since we focus only on gyroscope, even affordable smartwatches are covered here. This makes our solution quite unobtrusive and convenient to use, so you don't need to visit any clinical facility especially, and no one needs to be there for the measurement. You can the subject can do the measurement on their own. And second, in spite of all these, we have tried to keep the accuracy up to the mark, at least for upper body joints, for which we have tested our solution, and our mean error actually stands at just about 2 degrees in our experiments, and these experiments I'll briefly be touching in the next slide. And we have tried to build a real-time system, as in we have a very primitive dashboard, and where a specialist can observe the rotational parameters like speed and angle in real time as the rotation of the joint is happening, which can be really important and can help in pinpointing a particular moment in the rotational motion where say the joint is facing a greater difficulty while rotating. So that can be done by looking at the speed profile of the rotation, and to be precise, the real-time speed profile of the rotation. Then the accuracy of our solution is same whether the rotation is performed in any plane, because there is no dependence on accelerometer inputs. Either it's a vertical or a horizontal plane, the accuracy remains the same. So all the rotations that happen in horizontal plane, they also show good accuracy, like the internal external rotations we talked about a couple of slides ago. And also some other rotations can happen in horizontal plane if the user they prefer to be in some other pose. If you take an example, if the user is lying down, then if they perform shoulder abduction adduction, so that is going to be in a horizontal plane if the user is lying down. So it helps the user to be in any comfortable pose, this feature of our solution. Finally, at extremely slow speeds also, our system performs really well. In fact, most of our experiments they revolve around the speeds which are mostly around 10 degrees per second. And on the right you can see a very simplified diagram of our gyroscope based approach, the top right. And we use the axis angle quaternions to calculate the angle and instantaneous rotational axis. So when the session begins, the system estimates a reference axis of rotation along with the gyroscope bias, and thereafter the system keeps comparing the instantaneous axis of rotation to the reference axis of rotation. As you can see in the figure below, R is the reference axis, and Ri plus 1, Ri plus 2, all these are instantaneous axis for sample numbers I plus 1 and so on. Now as per the definition, the range of motion rotation is physically supposed to happen in one plane, right, because it is a single directional rotation. So we utilize that fact and keep estimating how close the instantaneous rotational axis is to the reference axis. On the basis of degree of proximity of both the axes, we calculate a confidence score, which is kind of really useful because it can tell in real time how well the user is performing the rotation. In other words, how well the user is staying in the same plane while rotating their arm. And they can kind of after looking at the confidence score, they can self-guide themselves to correct their rotational arc on the basis of this confidence score. So we'll see shortly this in a demo how that works. So here is how we designed a few pretty straightforward experiment setups for testing our system. And you can see we had a board with angles graduated on it as ground truth. And then we performed rotations at various angles, and you can see we tested our system both on the planes which were perfectly horizontal. We kept the board perfectly horizontal, and also as an inclined plane for internal external rotation. And then for the shoulder rotations for flexion extension and abduction adduction, so we cannot use the board there because that's due to the fact that the axis of rotation when you are doing shoulder rotation, it keeps translating. So we took measurements using a goniometer at a few landmark positions. There were 5 positions per rotational arc for shoulder abduction adduction and shoulder flexion extension. And you can see the results below where we achieve an overall mean error of around 2.2 degrees. And it can also be seen here that the errors in the experiments performed with the graduated board, for those experiments the error is actually lower than those for which the ground truth was taken from the goniometer. So that is because the board provides support to the arm to perform rotation in a constant axis of rotation, so the plane remains constant, so the system works really well there. But even in the other cases where we have used the goniometer, all the errors they are under 3 degrees, and those other cases actually are closer to the real world scenario, and which we find perfectly acceptable. So this error under 3 degrees, it's perfectly acceptable for real life use of the solution in range of motion analysis. And so as next steps, we already have plans in place to evaluate our system on lower body joints like the hip joint and the knee. And with our ties with a few ortho specialists, we'll be also testing our system for use with the doctors on real patients, and we're going to log the observations and improvements required when the system is used in actual clinical settings. So here is a small demo video showing a functional design of what our solution may look like, and you can see there is an integrated video feed of the subject also performing the rotation, and this can actually be really helpful in a telehealth scenario where the specialist can remotely analyze the motion in real time if that is a requirement. So here goes. So there's real-time speed, angle of rotation, confidence score, and the user is wearing a Galaxy Gear S2 smartwatch. So there's the user has now started the internal rotation. All the parameters, they are coming in real time. Now it goes to external rotation. So after coming back to the initial position, the system calculates the range of motion, as you can see. So that's 82 degrees and 50 degrees for internal and external rotation respectively. Now since we may have a few prospective clients, so we have filed a patent for this solution already. Thank you.